Hello, sir.
Hello.
Sir, can you hear
Yeah.
me?
So yeah, I can hear you. You had
Sir,
any
I have a
question?
question. Yes,
Yes.
sir. So in the previous lecture, you told that for the weak law of large numbers, the sample
Mhm.
mean eventually tends to the actual mean when n tends to
Correct.
infinity. Sir, I
Correct.
have read somewhere about gambler's fallacy. Like a gambler, he thinks that more and more turns he will take, and that will tend to mean, but it doesn't happen actually.
What is that? I am not sure. Um, so the point is, if the process is IID, right, independent and identically distributed, then the result essentially says that the sample mean should converge to the true mean asymptotically, right? Where in the sense, you can see this, right? So if you look at the difference, being greater than epsilon, that is the bad event, the probability of the bad event should go down to zero as n goes to infinity. Okay.
Okay, sir.
Yeah. So you said some gamblers. What is
Sir,
that?
gambler's fallacy. I read somewhere in
Fallacy.
the internet. I don't clearly remember, but I remember some of the statement like a gambler went to a casino and he like gambling, like tossing a coin or something like that. So he thinks
Mm-hmm.
that he is not winning. He is not winning. So he thinks that maybe I will uh, take turns more so that in the long run the mean gain will come. But it doesn't happen actually like that.
The
Mm-hmm.
gambler's fallacy is that basically every turn you have a chance of you double the bet which you have. So suppose you lose money now, you bet double or something like that. So eventually, whenever you win, you will win back everything.
Yeah. So that is the what is known as martingale, right? That situation. Okay. Anyway, so I'll look into it. I was not aware of this particular phrase. Okay. So shall we start? Are you okay, Rishabh?
Yes, sir. Yes, sir.
Okay. So in the last class we
Sir, I
looked
have
at, yes, Ayush, right?
sir yes sir.
Yes,
Sir, in the
please.
last class we
Uh-huh.
derived that the pack bound thing theorem. Sir, we have
Okay.
derived that probability of the estimated mean greater than
Mm-hmm.
delta is less than equal to expected
Mm-hmm.
exponential of negative of n delta square by 2 sigma square. So sir,
Okay.
is this a general like specific case of large law of law of large numbers?
Which one is a special case of large numbers?
This
No, so
pack bound.
no. So essentially, law of large numbers says that the sample mean goes to the true mean asymptotically in probability. Okay, so this is law of large numbers, called weak law of large numbers.
Yes.
The pack bound essentially says that with the probability of at least 1 minus delta, something happens,
Yeah.
provided if you have n greater than some number of samples. That is the general framework of pack. It's probably because with the probability of at least 1 minus delta, right? That fraction of the times it will happen. So it's called probably. Approximately, because whenever you state, you never say that the sample mean is exactly equal to the true mean, right? There is some fudge factor, so that's why it's called approximately correct. Okay. So
Yes.
you know, you might have, for example, if you had used some loose bounds to prove pack, then it says that even to achieve a smaller error with reasonable probability, the result may say that you need lot of samples, which may not be true in general, right? So there the tightness matters, right? The tightness of the bound matters, but here it doesn't matter. Asymptotically it should go to mean. At what rate, I don't care. Is that clear?
Sir, yes, sir. And the law of large number is like not just specific to any distribution. Like it
No,
is general to any distribution.
any IAD, yes. Okay, is that fine?
Yes, sir.
Okay, so we will start. So this is about the weak law of large numbers, right? One can show, of course, there are several examples that one can consider. Can somebody give me an example where xn converges to something in probability? Yes. Okay, so let's look at it this way. So, for example, I'll just draw in terms of picture. Okay, so x1 looks like this. Height is 1, width is 1. Okay, x2 looks like this. Height is 1. Let's see. Let me write the heights later. Half. x3 looks like this. 1 by 3, and so on.
Hello, sir.
Yes.
Oh, sir, PDF, right?
This is not PDF. This is the random variable. Okay, so I'll tell you what this is. 1 by n. Okay, so that means xn equal to xn of omega, right? Omega is your, okay, so let me start with the big picture, whatever, the entire thing. Omega, your experiment is between 0 to 1. Okay, that means, for example, I rotate a disk, I measure the angle, divide by 2 pi. That will be my omega, right? Small omega, any event. So you have this omega, and you have the density also. So basically, I can associate probability with this, right? So essentially, I'll assume uniform distribution. You know what uniform is, right? So what is that? So suppose I have a random variable. Let me call this as x, which is so x of omega equal to omega for all omega. Okay, this is a random variable. Right? Do you agree? I don't do any mapping. I just observe and call that as a random variable. There is a corresponding density, right? Fx of x. That is equal to 1 for all x in 0, 1, 0 otherwise. This is a valid density, right? So this is my experiment. I rotate the disk, scale by 2 pi. That's my observation. That is also a random variable in this case. And the density is uniform distribution. Okay. This looks like this, right? So fx of x, 1, 1. Okay. This is a valid density function. This is how I'm going to rotate my disk uniformly, randomly. Is that fine?
Hello, sir.
Any questions? Yes.
Sir, is this correct because the summation of fx, like summation of 1, goes to infinity?
Oh, no, right? Why summation integral, right?
Sir, integration fx dx should be equal to 1 for a valid PDF.
Correct. This
Here,
one,
sir,
right?
here you mentioned equal to 1 for all x belongs to 0 and 1.
Correct. Just integrate this function and tell me what the answer is. See, in the interval 0, 1, fx of x is 1, right? So it's integral 1 dx, which is 1, right? From 0 to 1.
Okay. Yes, sir. Okay.
It's a valid PDF. Is this fine, everyone? Okay. Now, with this, I'll take x1 as, now I'm going to define a new random variable. x1, it's 1 from 0 to 1. x2 of omega is half, 1 from 0 to half, 0 otherwise. 1 from 0 to 3, 0 otherwise. No, wait. How do I put it? Okay, so let me, yeah, so in general, I can just say xn of omega equal to 1 whenever omega belongs to 0 and 1 by n, 0 otherwise. Okay, this is my new random variable. Okay, but the way I'm rotating the disk is essentially uniform. Now, what does this xn converge to? Yes. What does that? What does xn converge to?
0, sir.
0 as n goes to infinity. In probability, well, looks like one might argue that deterministically also it goes to 0, right? But let's see. Let's look at the definition. So what does it say? Xn minus 0 greater than epsilon, right? So I have to look at all the events for which xn of omega is greater than epsilon, right? What is this event? This is nothing but the interval between what is this?
1 by n to 1.
No, it's epsilon to 1, right? This is the event, right?
Yes, sir.
So now, what is the probability of omega belonging to epsilon 1 under? So, how do I? Did I
So
make
1
any
minus
mistake?
epsilon.
Yeah, it's 1 minus epsilon, but did I make a mistake? No. Let me just think once again. I have to think one second. Did I make a mistake here? So I have to consider a sequence that converges to 0. So this is sorry, I think, okay, now let me just go this. It is all those omega for which xn of omega is greater than epsilon. So when will it be greater than epsilon? So xn of omega is like this, right? 1 from 0 otherwise, and epsilon is, let's say, here. Okay. So where is it greater than epsilon? It's between 0 and 1 by n, right? So this is nothing but probability that whenever omega falls in 0 to 1 by n, this xn is greater than epsilon. So what is the probability of this? So what is the probability of
1
this?
by n. 1
1
by
by
n.
n. So this goes to 0 as n goes to infinity, and it is irrespective of what epsilon is, right? So for every epsilon greater than 0. So that means xn converges to 0. This is a very, very, what do you call, trivial convergence, trivial result, okay? Can somebody give me, okay, so let's look at another notion and then maybe we'll come back, okay? So another notion of convergence is almost pure convergence. So some people call it as almost everywhere convergence, or there is another name for this with probability 1 here, okay? Because we are studying probability theory, okay? So definition is, we say that xn converges to x almost surely. This is how I'm going to write. If probability of limit n tending to infinity xn equal to x is 1. Okay, is this fine? It is all those outcomes for which the limit of xn of omega is equal to x of omega is 1. The probability of h is 1. Then we say that xn converges to x in almost sure sets. Okay, so let me try to give an example for this. Okay, okay, so something that converges Okay, so let me also state one more thing. So this is a fact. One can prove this. I'll leave it as an exercise. If xn converges to x almost surely implies xn converges to x in probability. Okay, it's a fact. I mean, it implies this. So the proof involves basically expanding this limit. So what is a limit? For every epsilon greater than 0, there exists a stage n such that xn minus x is less than epsilon for every n greater than that stage. That is the definition. You can use that to prove this. Okay. I won't prove this. So take it as a homework problem. Okay. Now let's try to understand what is this. So I will consider a sequence here. So let's say the first one is 1, 1. Okay. The second random variable is 1 till half, 0 otherwise. The third x3 would be half and 1. Okay. And fourth one would be 1 by 4, 0. Fifth one would be, what is the guess? Can you guess what is fifth one? Fifth one would be 1 by 4
by
to
5.
So half.
Oh,
No, it's half, right?
yes.
0. And so on. So after some stage, you have something like 1 by 2 power k plus 1 to 1 by 2 power k after some k stage or whatever, 2k stages. Okay, this is how the sequences are defined. Okay, now same experiment. So omega is 0, 1, uniform and uniformly distributed, uniform. Now what can you say about the sequence xn? What can you say about the sequence xn? What will it converge to? Suppose k is really large, the stage is really large. That means xn, n is really large. That means this k will also be really
Equals
large.
to 0, sir, only.
So what do you expect? Looks like
Vertical line only. Yeah.
like xn converges to 0.
0.
All of you are with me, or you have some issue, doubts? Any questions? Please ask. Rishabh?
So how did we? So we are just halving the interval.
Yeah, it's called a dyadic thing. So start with all ones, and then half till half it is 1, half to 1 by 1 it's 1, then 1 to 1 by 4 it's 1, 1 by 4 to 1 by 2 it's 1, 1 by 2 to 3 by 4 it's 1, 3 by 4 to 1 it's 1, then 1 to 1 by 0 to 1 by 8 it's 1, 1 by 8 to 1 by 4 it's 1, and so on. And then you come back, and 0 to 1 by 16 it's 1, 1 by 16 to 1 by 8 is 1, and so on. Keep on. So basically you are reducing the width of the pulse.
Okay, sir.
You can imagine, right? So you fix a width, move the pulse to the right, it hits 1, and then come back to 0, but you decrease the width, move back, come back, and so on. Okay, that is the sequence. So looks like this is, but in what sense?
Sir.
Right? Yes.
Sir, so the location of the pulse will depend on the value of k, right?
Exactly. Yes. In fact, it depends on the location of xn. So if you plot xn, the location depends on n, and also the width depends on n.
Yes.
Okay. So now let's see. So let's look at whether, in the usual sense, whether it converges to 0 or not. Let's say xn of omega equal to 0. Let's ask this question. Sumit, can you answer whether it is 0 or not? What is this convergence called? It's like
So
you're saying,
it is 0, sir. Yeah, it is 0, sir.
Suppose you have a sequence of functions. What do you mean by this? What kind of convergence is this?
So we have to check, like, it is a point-wise convergence initially.
Yeah, it is a point-wise convergence. So the question is whether you have a point-wise convergence. Do you think you have a point-wise convergence?
In obviously, sir, the limit you have given it implies it is a pointwise convergence. So we have to check if we know the function f and x, then
No,
one more is
you know
there.
the function now, right? Xn of omega is the function, and I have given
Yes,
that
sir.
here. Okay, so this is
So
I
we
don't
have
know.
to
This,
check
this
whether
is
it is a uniform or not. No, sir.
1, 2, 3, 4, 5.
Hmm.
Huh?
So we have to check whether this function is uniform convergence or not, sir. This one only.
No, just answer me whether it is a point-wise convergence.
Yes, sir. Obviously, it would be the pointwise convergence
Why?
because,
Okay,
sir,
so others
the
to be on the same page. So let me explain what is convergence of functions. So for example, you have, let's say, a function sequence of functions. Okay, so let me use a different color. So let's say this is your function to which it converges. Okay, so now you have this thing, and then we have this thing, and then finally it goes like this. And then last one will convert like this. So now this, okay, so let me use maybe different color. So this is f1 of x, this is f2 of x. No, is that correct? No. Let me call this as f2 of x, this is f3 of x, and let's call this as f 10 power 8 of x, okay, and so on. Okay, so what do you mean by fn converging to fn of x? So this is, let me call this red function as f of x. So now I'm
Sir,
asking,
hello, sir.
yes,
Sir, a function is fx. Sir, what is n is in a particular function?
this is different functions. F1 of x is one function, f2 of x
Okay,
is
okay,
another
okay,
function,
okay,
f3 of
okay,
x is another function, and so on. I take a sequence of functions.
okay, sir. Okay, okay.
Okay, so now what do you mean by fn of x converging to f of x? You know that 1 over n converges to 0, right? You have a sequence of numbers, and you know what do you mean by a sequence of number converging to some number, right? That notion you know. But what do you mean by sequence of functions converging? So that essentially means that you fix, for example, x naught here, okay? And everybody can see this, right? Let's look at the vertical slice. So what is this? So what is this, for example? This is f1 of x naught. This is f2 of x naught, and so on, right? So for a fixed x naught, I get a sequence of numbers because f1 of x naught is a number, f2 of x naught is a number, and so on. And similarly, f of x naught is also a number, right? Now I can ask whether fn of x naught converges to f of x naught, right? If so, then we say that a sequence of function fn of x naught converges to f of x naught at x naught, I mean, that particular value, right? Supposing this x naught, the choice of x naught is irrelevant. For example, you pick any point x, fn of x converges to f of x, then we say that the function fn converges to f of x pointwise, because every point, if you look at it, the sequence seems to go closer and closer to the function f of x. Is this fine? Is this fine or no?
Sir, what is the opposite of that? A function can be convergent for a particular point also, like a sequence of functions.
Can happen. Then you cannot say that it converges pointwise to f of x. You cannot say that.
Okay, okay.
Right? Yeah. Okay. So now, Praveen, are you with me or?
Yes, sir. Yes, sir.
Okay.
Sir, one thing, sir. So in case of the sequence of functions, sir, the functions, all the functions are defined under the same domain, no, sir?
Yes.
So in case of the, sir, random variables you are taking, so that's all the random variables should have same sample space.
Yes, that's what I'm considering.
So whatever we are doing, all are on the same probability space, no, sir?
Correct. Exactly.
Okay, sir.
Okay, so you understood what this means, right? This is called pointwise. Okay, now let's look at this sequence. Okay, so let's look at this sequence. Suppose I pick a point. Okay, so let's suppose I pick some point here. Okay, this is some point. I want to see whether x, so this is some omega naught. Okay, now let's look at what is xn of omega naught. Well, in this case, it's 1. Maybe xn plus 1 of omega naught is also 1. But after some time, what happens? This thing will move, right? Do you agree?
Yes, sir.
Yes, sir.
So it becomes 0, right? This moves here and
Yeah.
so on. And it comes back here, right? This is what you get after some time.
Yes, sir.
And then this small pulse will also move. After some time, you get 1, right? If you look at sequence xn of omega naught, what is it that will have 0, 0, 0, etc. Then there will be a 1, 1, 1, and then there will be a 0, 0, 0, 0, etc. And then suddenly 1, 1, 1, lot of ones. And then there will be a 0, 0, 0, 0, 0, 0, 0, and then suddenly lot of ones, and then 0, 0, 0, lot of zeros, and then
Sir,
uh,
this random variable, it just lies within an interval 1 by 2 power k plus 1 to 1 by 2 power k, right? And k is the sequence number, like.
no.
Okay, could you just show that again? Like,
To be very precise, I think it will be, see, first one, see, you should look at this one, fifth one, right? This is fifth one, or
no, sir, could you just show
1,
the definition of the
2, 3, 4, 4, fifth one. This is fifth one, right? So fifth one would be 1 by 4 to 1 by 2, right? So it's 1 by 2 square to 1 by 2.
okay. So like, could you show the definition of the random variable? Like,
There is no, I haven't defined it. This pictorially I have defined, that's all.
okay, fine. Okay.
Yeah, you figure out. So I'll ask, this is an exercise. Look at the pattern and define what this is in terms of the index n. Okay? Is that okay?
Okay, sir.
Oh my God, what happened? Oh God. Oh, great. I hope it is saved. Okay, good. So you understood, right? So what I get is a sequence of zeros, and then 1, 1, and then sequence of zeros, and then I'll get lot of, maybe multiple ones, sequence of zeros, and then lot of ones, and then sequence of lot of zeros, and then sequence of lot of ones, and then sequence of lot of zeros. What does this sequence converge to? It doesn't converge to anything, right? It neither converges to 0 nor converges to 1. Do you agree?
Yes,
Sir,
sir.
but for a fixed omega, sir. So suppose you are fixing one omega,
That's what I'm
and
doing.
after
Omega
and
naught is what I'm
yes, sir, and we just take the n very large, sir.
correct.
So after some time, sir, that omega naught will just come out from that interval, that is 1 by 2 to the power
But it will
n.
come back, right? See,
Yeah,
this
then
one
it
is
will
also
only
moving
give
and
0.
coming back, right?
Sorry, sir.
It is moving and coming back, right? That function.
Oh, so yeah,
Yeah,
so we have to just
lot of zero, and then there will be lot of ones, right? And then there
okay,
will be
sir.
too many zeros and then too many ones. So it keeps on fluctuating, right?
Sir,
Okay, so it just
Yes.
so can you please tell how we are writing the sequence here?
This thing, xn of omega,
Yes, sir.
this is x1 of
yes,
omega,
actually this interval we are not getting, I think.
this is 1, okay?
Something, yeah,
Yes, sir.
This is
then we
x2
just
of
divided
omega.
it. Hmm.
From 0 to half, it is 1, 0 otherwise. Do you agree? Okay?
Yes,
This
sir.
is x3 of omega. This is from half to 1. It's 1. Okay? x4 of omega. This 0 to 1 by 4, it is 1. 0 otherwise. Okay? x5 of omega. 1 by 4 to 1 by 2, it is 1. Okay? Otherwise 0. x5, x6 of omega. Okay, 1 by 2 to 3 by 4, it is 1. Okay, x7 of omega, I'll write it here somewhere. X7 of omega is what? It will be 1 whenever omega belongs to 3, 4 to 1, 0 otherwise, right? What is x8 of omega? 1 whenever omega belongs to 0 to 1 by 8, right? 0 otherwise, and so on. I'll keep on doing that.
So it means we are just
Hello,
dividing
sir.
those intervals 0, 1 into the dyadic rationals in bit 0, 1, no, sir?
Exactly, yeah, that's what
Numbers,
I'm saying.
yeah.
Yeah.
Okay, sir, okay.
Hello, sir.
Yes, tell me, Rishabh.
Sir, if we increase that n,
Ah.
so sir, the width is also decreasing the pulse. So sir, the
Exactly.
probability of happening one will be less than zeros. Like there will be more
Yes, sir.
zeros than ones for a fixed omega naught.
Correct, good. So that's what is happening, right? You'll have lot of
More
zeros
ones.
and ones. Lot of zeros and
More
ones.
ones
The
will
number
come.
of zeros will increase, keep on increasing, right? Each time you increase n, I mean, if you look at the sequence, there will be lot of zeros and followed by lot of ones, but the number of zeros will be too much, right?
Yes, sir.
Now the question is, yes.
A lot of ones should come initially in the initial sequence
No, it depends on where
because
you
the
take.
width is decreasing.
No, it depends on where you take that omega naught, right? Of course, the first one will always be 1, right? x1 of omega is 1 for all omega, so it should be 1, right?
Yeah.
If I take omega naught to be 3 by 4, what will happen? 3 by 4 is here, 1. 3 by 4 is here, 0. 3 by 4 is here, 1. 3 by 4 is here, 0, right? 3 by 4 is here, 0. 3 by 4 is here, 1, and so on, right? Can you imagine? So it's like pulse moving, then shrinking, moving, shrinking, moving, shrinking, and so on, right? The width is decreasing, but also it's moving back and forth. Each time it comes back to 0, it will shrink. And then it will keep on moving in the same width, whatever. Is that okay?
Yes, sir.
Rishabh, Ayush,
Yes, sir. Yes.
Nitish, Jayant.
Yes.
Yes, sir.
Yes, sir. Okay. Okay, now what do we conclude? Limit n tending to infinity, xn of omega is not equal to 0. This is what we concluded, right? Do you agree?
Yes, sir.
Yeah, it doesn't converge
Yes, sir.
to 0 point-wise. That means you take any point, you get a sequence of ones and zeros, it will never converge. It will, no matter how far you go in the sequence, there will be ones appearing later. There will be zeros appearing later. Therefore, you cannot conclude on convergence. So it doesn't converge, right?
Yes, sir. Yes,
So
sir.
that means you look at all those omegas in omega such that limit. Okay, I think I have to connect to the battery. Xn of omega equal to not equal to 0 is what? What will be this one? 0, 1, right? It does not converge anywhere.
Yes, sir. Anyway, yes, sir.
So now we should look at probability of this thing. Is what?
1.
Yeah. That means probability that xn does not converge to 0 is 1. So what can you say about probability that xn of omega xn converges to 0? Is 0.
1, 0.
Right? Therefore, this implies xn does not converge almost surely to 0. Do you agree with this?
Yes, sir.
Yes.
Yes, sir.
Right? Now, can you think of whether it converges in probability? What is convergence in probability? You have to take xn minus 0 greater than epsilon, right?
epsilon.
So
Yes,
you look at all the omegas such that this happens. So this set, how Nitish, can you tell me what this set is? Nitish, are you there? Nitish Kumar.
Hello.
Okay, Jay, yes. Can you tell me what is that set? This thing. Hmm? Yes. What is this set?
Sir,
Yes.
it contains all the omega such that xn of omega is greater than epsilon.
That is
Means in
correct.
that graph, sir, in the above graph, you explained one. Let's take x3 of omega. For
So
all
let's
those,
take
let's
epsilon.
that's the
Epsilon.
epsilon. Yeah.
It is all those omega for which xn of omega is greater than epsilon. So what
So
will be that?
omega is between 1/2 and 1.
Exactly, right? Okay, what about x by 4? x4 of omega, sorry, not x by 4, x4 of omega. It
0
is
to 1/4.
okay. So in general, what can you say? Set of all omega such that xn of omega is greater than epsilon. What can you say about this? Difficult, I mean, I haven't written this. It will be 2 times some k plus 1 to 1/2 power k. Do you agree?
Yes, sir.
Right? Well, after a long, if n is very large, you will have a small region over which this, so let me just generalize this, okay? So let me call this as, okay, so let me call this as kn plus 1 to kn, okay? So kn is some sequence that goes to infinity as n goes to infinity, okay? This is what we have. Is this fine, Nitish, Jayant?
Yes, sir.
No?
Yes, sir.
Nitish, is it fine? Nitish? Yes, sir. Okay. Now, what will happen to the probability of this set of all omega such that xn of omega greater than epsilon is what? It's nothing but probability falling in this 2 power kn plus 1 to 1/2 power kn, right? So what is the probability that omega falls in this region? Very small region. Huh? See,
Just length of the interval, sir.
yeah, probability is uniform, right? This is the density. So if you take a small strip, the probability that it falls there is nothing but the length. The length is 1/2 power kn plus 1, right? But as n goes to infinity, what happens to this? Yes, what happens to this?
0, sir.
Right?
Zero, sir.
So that means probability, this implies probability that xn minus 0 greater than epsilon goes to 0 as n goes to infinity. What does this imply? Xn converges to 0 in probability, but xn does not converge almost surely to 0. Is that fine? That is why this is called weak and this is called strong. Okay? Because one implies the other. So almost sure implies improbability, but improbability does not imply almost sure. This is a counter example. Okay? So the next homework that you are going to submit in a couple of days is to make this very formal. You have to write the dyadic functions properly, label the width, everything, so properly and show this. Okay, I have pictorially shown this. Hopefully, I have convinced you that this is correct. What you have to do is formally write this.
Hello, sir.
Yes.
Sir, is this not a general intuition or probability that like we do not know the exact, but we can somehow predict or something like that?
No,
Like
so what is this saying? This is saying the places where it doesn't seem to converge to zero is of very low value to me, right? Because it has probability zero occurrence, so I don't care. Most of the places it converges, but only in the place where of small width it doesn't. I don't care about that. Okay, but almost sure is saying something. I want this to happen not only in the places where I don't, where I care, but also it should happen all the time, right? Do you agree? You
yes,
understood
sir.
the difference,
Yes, sir.
right?
Yes, sir.
Yeah. So that is the
Sir,
difference. Okay. Yes.
sir, here in this question only, like
Uh-huh.
xn is equals to 1 in a small range of omega, right?
Correct.
So here, what does this mean? Xn tends to 0 in probability means, are we saying that probability of xn is tending to 0?
This is what we mean. So probability of xn greater than epsilon goes to zero as n goes to infinity for every epsilon greater than zero. That's what we are saying. So it is
So this is
all
a
those
notation.
cases where xn is larger than epsilon, that means it violates the fact that xn converges to zero, has insignificant probability. That's what we are saying. Okay? Is that fine? The places where it doesn't converge to zero has very low probability. That's what we are saying. Overall. Is this okay or no?
Yes, sir. Okay, sir.
Okay, but remember, because the function is moving back and forth, even though the width decreases, almost sure is not guaranteed because it's not true, because it's not happening. Suppose I go down the sequence, it's not happening almost surely. I'm not confident because there might be some men for which suddenly it becomes one, and I can't be very sure. Whereas in terms of probability, yes, I don't care, right? Okay.
Also, sir, if epsilon is you have written that epsilon is greater than 0. If we say
Huh.
epsilon is greater than 1, it will be almost sure it will be 0.
That's why it should be for every epsilon greater than zero. It's not for some epsilon that you give. It should be true for every epsilon.
Okay.
Okay.
Yes.
Is that fine?
Yes, sir.
Okay. Okay. So this is there is a result called strong law of large numbers. Strong law of large numbers. Okay. It says the following. Let x1, x2, etc., xn be IID random variables with finite mean and variance. Then 1 over n summation I equal to 1 to n xi converges to expected value of x1 almost surely. Okay, earlier we had proved that it converges in probability. That is why it's called weak. Now one can prove that it converges to the mean, the true mean almost surely, which is a stronger version of law of large numbers. Okay, that means you can expect, no matter where you look at it, you can expect this to happen with high confidence. Is this okay? You understood what is the difference here? Exactly the same result as that of weak law of large numbers, except for the convergence in probability, we have replaced it by almost sure. Yes, somebody wanted to ask some questions. Praveen?
Hello. Yes,
Yes.
sir. So almost surely means probability that this converted to E of x1 is 1, or it is almost 1. Right?
No. It's exactly 1. Okay, I'll write it.
Exactly. Okay.
Yeah. 1 by n summation I equal to 1 to n xi equal to expected value of x1 is exactly equal to 1 in the limit. So this is what it is. Okay, is that fine? Is that fine, Praveen?
Yes, sir.
Okay. So this is almost sure. So now the question is again, how do you prove this? Before proving this, let me give you a few other results called Borel-Cantelli lemma, which is okay. Savan, do you remember this? What does Borel-Cantelli lemma says? Is Savan there?
Yeah, yes, sir. Not really, sir. Remember that much.
Huh? Okay, so suppose I take a sequence of events, okay? So A0, A1, etc. Whenever I say event, it should belong to the sigma algebra, okay? Sequence of events. If I were to make statement like AN, the sequence occurs infinitely often. What does that mean? Okay.
Probability of AN is 1.
Huh?
Probability of AN.
No. So I'm
Sir,
saying,
happening of A is so
okay,
not happening of A is finite, sir.
okay. Now let me take an example maybe. How do we put it? Let me just, instead of, I'll start from 1, okay? Instead of A1, A2, etc. Okay? Just give me a minute. I'll think about an example just to explain this. Okay. So let me give you an example. So suppose I have a typewriter. Okay. I have a lot of typewriters. Okay. In fact, a lot of them. Okay. And I have monkeys sitting in front of it. Okay. And they are randomly typing the typewriter. That means they are typing something. Okay. Now, let me call the event A1 as the event that the first monkey types Shakespeare. Let's say, which is your favorite novel or something? Anybody reads novels? Okay, Rishabh, do you read? Okay, so let me assume that since this is probability course, now A1 be the event that the first monkey types Gallagher's book on stochastic processes with a theory for applications, right? Verbatim, exactly like that. Okay. A2 is the event that the second monkey types this, the same book. A3 is the third monkey, AN is the nth monkey, and so on. Assume that there are infinitely many typewriters with infinitely many monkeys. Okay. So what do you mean by AN occurring infinitely often?
It's not happening of A is finite, sir.
No. So essentially, if you look at this whole thing, right, till infinity, one of the events should happen. Okay, let's suppose that. What does that mean? That means at least one monkey is typing the Shakespeare. Okay.
Yes.
So that means A1 should occur, or A2 should occur, or A3 should occur, and so on, right? So one of the things. This should occur, right? But that doesn't guarantee that there are infinitely many monkeys typing Shakespeare, right? You agree?
Sir, what is A1, A2? Like every monkey is typing Shakespeare.
No. A1 is the event that the first monkey types Shakespeare or stochastic processes book?
Yes, yes. A2.
A2 is the event that the second monkey types Shakespeare or stochastic processes.
Okay, okay.
Okay, if I say A1 or A2 or A3 and so on n to infinity, that means at least one monkey would have typed Shakespeare. Okay. Now, if an were to occur infinitely often, that means you should expect infinitely many monkeys to type Shakespeare. If that were to happen, what should happen? If you look at this sequence, right, from A2 to A infinity, one of them should happen, right? Okay. Right? Sorry, A equal to 2 to infinity. So if you start from second monkey to infinity, this should happen.
Yes, sir.
Okay, so both should happen, right? If there are
Yes, sir.
infinitely many monkeys typing, if you look at from A1 or if you look at from A2, it doesn't matter. So both should, at least one monkey in the infinite set should be type Shakespeare. If you start from 3 also, it should be
Yes,
this,
sir.
and so on, right?
Something supremum like term will come, no, sir, I think.
There is no supremum, right? An event is
Limit supremum something, sir.
okay, so let's okay.
Yes, sir.
Okay, so what is this? This is intersection k equal to 1 to infinity union I equal to k to infinity, right? AI, right? This is the event. Now, what do you mean by infinitely often, occurring infinitely often? The probability of this should be 1, right? If probability that k equal to 1 to infinity, I equal to k to infinity AI is equal to 1, we say that AI occurs infinitely often. Is this clear?
So yeah, this same term, that intersection and union of AI, it is termed by the limb soup of
Yeah, you
something
can.
AI, sir. You can
Okay, so
directly
let me
write
not.
it.
Yeah, true. The right limb soup of AI, that means
Yes,
this,
sir.
but limb soup has other meaning. So you cannot actually define limb soup for a sequence of events. You can look at numbers and say sequence of numbers and say limb soup limit, but not here.
No, sir,
So
instead of sets, we can also write, sir. Like the term you were used, no,
that
sir,
is
that
that is
it's
just
infinite.
notation, that's all. So this is the
Yes,
notation for your limb
yes.
soup. So let me not use one more notation. So this is
Okay,
what
sir.
it is. Okay.
Yes, sir.
If this happens, we say that this is AI occurs infinitely often. Okay.
Okay, sir. Hmm.
Okay. Now, if you go back to the previous example, suppose let's assume. So let's see what is the probability that A1 will happen. You know what A1 is, right? Monkey should type the entire Shakespeare. What do you think is the number? Huh? How do you calculate that? Can somebody tell me? Suppose, let me make it even more simpler. So let me assume that it has to type one page of some, let's say, stochastic processes, page number 7. Okay. Let's say plain English, no LaTeX, nothing. Okay. So how do you compute? In a typical page, how many words will be there? Or how many sentences will be there? 20? Let's assume 20.
Okay, sir.
In each sentence, how many words will be there? How many characters?
Maybe, sir, 7 or 8 or 10.
Hey, how come one sentence you have 7 or 8 characters? You write one sentence.
Like
You
4 to
have some
5.
30, 40?
3 to 4.
30, including space and everything, tabs.
Okay,
30,
okay. Achha,
30
oh,
letters.
characters, sir. No. Okay, sir.
Yeah, 30
It's
letters.
character.
Okay. 30 letters into 30 letters into how many lines?
20.
20.
20
So
sentences, sir.
600 characters per page, right? What is the
Yes.
probability that you exactly type those 600 characters? So each letter, it can be one of the
26
26
plus
letters,
6.
right? A, B, C, D, and so on, one of the 26,
Hmm.
right? What is the
Hmm.
probability that the monkey ends up typing all the 600 letters exactly? It's 1 by 26 power,
1 by 20. Yes.
600.
right? How small is this?
Very small, sir.
Very small, right? It's like 26 power 600 is astronomical. So 1 by that is like more than, smaller than microscopic, right? So it's so small. But in principle, do you think that one monkey would have always written, or infinitely many monkeys would have written Shakespeare in this infinite sequence of typewriters? What is your guess?
No, sir. So
No, how many
infinite.
think that, so there are infinitely many monkeys typing Shakespeare. The question is it possible that infinitely, if you do this experiment, you'll end up seeing infinitely many Shakespeares written by infinitely many monkeys? Not all monkeys, by the way, but there will be infinitely many subset which would have typed Shakespeare. What do you think is the answer? So, Rishabh, what is your guess?
Sir, when you consider infinity, then there is a chance that maybe there will be some monkey.
Not some,
There will
I'm
be
saying there will
monkeys.
be.
Monkeys. There will be infinite monkeys that will type infinite.
Okay, what are the chances? If I do this experiment in, let's say, 100,000 parallel universes, in how many universes you will find infinitely many monkeys writing, typing Shakespeare? Praveen,
Yes, sir.
any thoughts? Hey, Ayush, you should tell me, man. So you have taken my course. I have taught this at the undergrad also, level also. Ayush,
Yes, sir.
what is the
Sir,
answer?
I
Huh?
forgot that.
No, how can you forget? Okay, Nitish, any guess? Hmm? Jayant?
Will it be close to 0, sir?
Okay. Okay, so the surprise is in all 100,000 universes, there will be infinitely many monkeys in each one of them typing Shakespeare. That means with probability 1, infinitely many subset of monkeys would have typed Shakespeare. Okay, that is the result which we are going to prove in the next class. Okay, so let's
That is
prove
because
it.
we are including the infinity, sir, right? If
Yes.
there is not the clause infinity, then we cannot state this statement.
Yes, true. True. Of course, these are asymptotics, meaning infinite. But what does it say? If you have some trillions of monkeys, then many monkeys would have typed close to Shakespeare. That's what it says, right?
So this
If
sounds
limit A1
trivial
to
sometimes.
huh?
So this sounds like kind of not trivial or not. But this sounds kind of sure, like given infinite chances, there must be. So is there kind of mathematical proof of this statement or theorem?
That's what I'm saying, right? We will prove that in the next class. Prove
Okay.
meaning proof. Mathematically prove that this is true. Okay. Okay. We will prove that there are infinitely, it's possible. Okay.
Hello,
Is
sir.
that right? Hmm? Yes.
Sir, so the number infinity associated with number of monkeys is less than the infinity the associated with the number of trials. I mean,
What
two.
trials?
Here we are talking about two infinities, right?
No. So one infinity, of course, 1, 2, 3, etc. is also infinity, right? There are infinitely many such numbers. How many even numbers are there? Infinity,
That's what I'm
right?
telling, sir.
So subset,
It's
yeah.
like,
Yeah. If all alternate monkeys type Shakespeare, then there'll be infinitely many. But not all monkeys would have typed Shakespeare.
yeah.
So what I'm saying is there are infinitely many.
Yeah.
Okay. Okay. So we will prove that in the next class. I'll stop here. This is interesting, right? How many of you think that it's not interesting? Rishabh, you think it's yeah, it should happen?
So I turn on the microphone for to say that yes, it is interesting. Then you would
Okay.
change the question like no.
Okay. Okay. So Sumit,
Yes, sir. Sir, actually, in sir, realizing I am getting something like the infinity by infinity like structure. So,
why?
because sir, the happening of those events are like infinite. The chances are infinite.
Chances
And
can never be infinite, right? It should be between
like
zero
the happening of that event, like the typing the monkey one is typing the Shakespeare is means one is also typing, second monkey is also like
not
sir,
all.
I'm just
Not all. It could be all
means
prime numbers.
infinite number, no sir.
Yes, it is infinite number.
So sir, your question was that what are the chances that they
No,
will
no. What I'm
type?
saying is whether there exists a subset of infinite monkeys typing
Yes, sir.
Shakespeare. The chances is 1.
Yeah, so while giving the answer of this question, so we are just I'm just considering the probability, like we said, number of favorable chances divided by the total sample spaces. So in that sense, I'm getting something like infinity by infinity cases, like
You can never
that
get that,
answer.
right? Infinity by infinity kind of thing.
Okay, sir.
We will see in the next class, huh?
Okay, sir.
Okay. Nitish, Jayant, is it okay?
Yes,
If
sir.
there are no questions, then I'll stop here.
Yes.
Okay. Okay. Yeah. Thank you.
So,
Shyam?
hello. Yeah.
Yes.
So that homework, have you seen it? Or I sent a
Which
mail
homework?
yesterday. Sent a mail yesterday.
I saw that. Yeah.
Yeah. So I'll send that.
Not
Is it okay?
uploaded, right? So yeah, you
I
can
want.
send it to them. You can send it to them. Yes.
You
I
saw the
thought
question.
yeah, I saw that question. So the xn plus y and converted to x plus y, these kind of things, right? Should be
Yeah.
okay.
Okay.
Yeah.
Okay.
Okay. Yeah.
Okay. Bye.
Okay. Thank you. Bye.
Thank you, sir.